In this tutorial, I explain how to implement the recursive fork-join pattern in the chemical machine. The recursive fork-join pattern is something that's not very easy to implement without more advanced functional primitives such as futures or other asynchronous effect frameworks. Let us begin just by illustrating what is the recursive fork-join pattern by looking at the non-recursive fork-join pattern. It is also known as MapReduce. What it is that we have a task that can be done sequentially, or it can be split into two subtasks, which we call forking because these subtasks are executed in parallel. But the subtasks themselves are never split. They're never further split into smaller subtasks. So those subtasks are executed sequentially. Their results are merged into the final result for the entire task. Now, how exactly we split a task into subtasks, how exactly we perform a computation sequentially or merge the results, that depends on the specific computation. But this pattern repeats generally for all such computations. A simple example of a non-recursive fork-join pattern is a ternary search. Now, binary search is something that cannot be parallelized very easily or very naturally, because in a binary search, every step depends on the completion of the previous step. But ternary search can be parallelized, and here's how it works. We need to find an element in a sorted array, so let's visualize some array. We split the array into three roughly equal parts. And then, for instance, we want to find an element x. We compare these elements with x and find out if x is less than this, or greater than this but less than this, or greater than this. And so we find out in which third of the array the element x might be. And that gives us an array 1/3 of the initial size, which we again subdivide into three parts and so on. So that's the ternary search, and every time we split an array into two parts, we need to compare x with two different elements of the array, and these two comparisons can be done in parallel in a trivial fashion. And then once you have the results, which are Boolean, is x greater than or not than this element, then we merge these two results in that we decide in which part of the array we should look next. So we can visualize the computation like this. We start with the initial value. Let's remove this x here. It's actually not very helpful. So by x here, I mean the initial data for the task, which would consist, for the ternary search example, from the entire sorted array and a value for the element that we're looking for. So that's the initial data. And then we decide to fork, so we split into subtasks. Let's, for simplicity, say we split into two subtasks, like in the ternary search, we would have two subtasks. Each subtask has its own data and is decided sequentially, so it's done sequentially. Each task is a comparison of the comparison of the element you're looking for with this element of the array, and that is sequential. So we perform these tasks, they're done, and we have a result. Then there's a merge step that takes the two results and merge them. And the result of the merging is some new data, which would consist of a smaller array and the element we're looking for. And then we again fork and merge. So the merge is called join also, so hence fork join. So we fork and then we join, and we fork and we join. So in this case, as I already said, we never split a subtask into further subtasks. So this is what I mean that this fork join pattern is non-recursive. So we fork, but we don't fork again ever. So we fork and then we join. Then we can again fork on the big task and then we join. So that's a non-recursive case. Now the recursive case is very similar, except we are allowed now to fork subtasks further, subdividing them into sub-subtasks and so on. And there is no limit in how deep we can go to split into subtasks. We split until it makes no more sense to split. So in practice, we split until the tasks are small enough to be done sequentially with not much overhead. An example of recursive fork join pattern is parallel merge sort, where we split an array into two subarrays, roughly equal size. We sort each of the subarrays, and then we merge these sorted arrays into one big array. Now the sorting here is done again in the same way, and so this subtask for one subarray will be again split into two smaller subtasks, or sub-tasks, so to speak, and so on. And so the splitting will be done as many times as necessary until the arrays are very small, and so that they can be sorted efficiently without parallel computation. And so the computation would look more like a tree than like a line here. This computation is more or less a straight line with these fork join stages. And this computation is more like a tree. We fork, but then we fork again, and when we join here, we need to join these two, but not this, because this is a higher level fork. So this needs to wait until we're done here with this join, and then we merge it with this result. So this result just stays here, waits until these are done. So this is a much more complicated organization of the computation. Let's see how we can implement this using the chemical machine. So what we will implement is a generic fork join. That is, we're not going to implement a specific computation only. We're going to implement a general pattern, which can be then instantiated for a specific computation. And the pattern is parameterized by two functions, fork and join. And the fork function takes the task, which is data of some type A, and it decides whether it is necessary to split the task further or not. If not, it means we can compute the result sequentially, which was the D step here, just done right away with no parallelism. And if it is not so, then it needs to be split into a list of subtasks. For simplicity, I'm using the same type A for the task and for its result. I just don't want to overcomplicate this tutorial, because it would be easy to refactor this into as generic as possible. So, for example, this would be our Fibonacci number computation that takes an integer and returns an integer. But that is not essential. We could easily generalize this to arbitrary types or type constructors or whatever. But the main important characteristic of this pattern is that this fork function will decide, based on the value of the task data, whether the task needs to be split or not. So this decision will be performed after we see the data. And so it must be a function from the data to a disjunction of a result or a list of tasks. The join function takes a list of results and produces a result. So if these two functions are implemented, then what we are supposed to do is to make a fork join runner that will take these two functions. It will take the initial value of type A, and it will perform everything in parallel and return the final result. So this kind of roughly designed function signature is what we're looking for. And if we implement this run fork join, then all we need to do is to substitute specific implementations of computations fork and join, and then the pattern is already implemented. So for instance, the Fibonacci numbers are computed like this. So the fork will decide if the integer x is small enough, then we know the Fibonacci result is 1. Otherwise, we split into x minus 1 and x minus 2 tasks. And the join consists simply of adding the partial results. So this is the way that we formalize the Fibonacci recursive definition, which is fn equals fn minus 1 plus f. I should maybe write it in a more mathematical notation. So this is split into two parts, into fork and join. So let's begin by implementing this without any parallelism at all. So this is a simple task to implement. We take the initial value, we evaluate the fork function. If the fork function gives us a left, that means we are already done, we return the result. If the fork function gives us a right with a list of subtasks, then we perform a map over the subtasks. For each subtask, we run the same function, and that will give us a list of results, and we join that list of results using the join function. So that's really easy, and we run the test for some Fibonacci numbers, and I also added timing, which we will run later when we see all the other implementations. The second implementation I decided to put in is the standard Scala Future. So it's very easy to put parallelism into this code because Scala Future is applicative, and so we can easily parallelize futures. And the join is also easy because future has this method, future.sequence. So all we do here is we replace this join of the result with map of join, because now we're going to return a future of A instead of A. and we use a future sequence on a sequence on a sequence of futures here to convert them into a future of a sequence. I'm not going to talk much about this implementation because futures are standard, and certainly this code is simple enough. It's just a simple translation of the non-parallel code using futures. And I run the same tests. Now let's implement the fork join pattern using the chemical machine. Certainly, the chemical machine is a very general concurrency method, and it is not specifically adapted to fork join or to any other concurrent pattern, but nevertheless it's easy to implement by hand. Certainly it would be much more difficult for us to implement this by hand, future.sequence, from first primitives, from just having future and future.map and such. It would be much more difficult for us to do that. If you look at the result, the code, then there's a lot of stuff here that needs to be done. How do we implement the fork join using the chemical machine? So let's derive the implementation by reasoning. Now the reasoning in the chemical machine is based on the idea that we need to look at data, and we need to think about data as living in a concurrent world and being consumed by concurrent processes. So it's a data-driven reasoning. So what is the data that we need to manipulate when we do a fork join? Well, obviously there is this initial value, say x, and the final result that is obtained after the computation. So the initial data needs to be consumed and the final result needs to be delivered. Now it means in the chemical machine these are data that is carried by molecules. The data that are carried by some molecules, say start and report. Well, all these would be names of these molecules. There's no other way in the chemical machine to manipulate concurrent data except by putting it on a molecule. So we don't have to think very much at this point. Let's define these two molecules. And the start molecule will be such that when we emit it with some value x on it, then some reactions will start. They will consume this molecule, and maybe some more reactions will later start, and then eventually this molecule will be emitted with some result value on it. Say so what happens when a task is split into subtasks? Well, clearly each subtask needs to again emit the start, because we don't want to define new procedures every time. We want to parameterize this and make a recursion of some kind. So obviously, if we are able to implement this fork join using molecules, then we can just reuse the same molecule to start the fork join on each subtask. Now, the problem, however, is that the subtasks should report their results separately from the main reported result. So if you look at this diagram, this subtask needs to report its result here to some computation that will wait for another subtask's result and merge them into a bigger result. So this subtask needs to report to somebody else, and the entire a final result needs to be reported into some third molecule. So all these molecules need to be different. So all these report molecules have to be different. Otherwise, we can't distinguish subtask results from each other, from subtasks at different levels, and from the full result. So an easy way to implement this is that we can define a new report molecule with its own new reaction every time a task is split into subtasks. Alright, so we will do that. Now, another consideration is that the results of subtasks need to be accumulated, put into one big list. Again, in a chemical machine, the only way to do such a thing is to put this data in a molecule. So since we're manipulating this data, it needs, in a concurrent fashion, it needs to be data on a molecule. Alright, call this molecule accumulator. Now, finally, let's think about how we can expect start to know which report molecule to use. Now, if we want to start a fork join process for a subtask, we emit start, but the subtask should report the results in a different molecule than our own overall report molecule. So the reaction that consumes start needs to know which report molecule to use, but it cannot know unless this report molecule itself is part of the input data for that reaction. Therefore, we need to pass the report molecule emitter as a value on the start molecule. The report emitter has this type. Therefore, the type of start must be a tuple of x, which is of type A. Result is also of type A. So the type of start must be this. It's a tuple of A and emitter of A, which would be the report emitter. So we need to pass the report emitter together with the initial value as a tuple on the molecule called start. So at this point, it seems we're done with the design. We know what molecules we need and what reactions they will have. So let's just write it down. Start is this molecule with this type. It will carry this tuple. It will have a reaction that decides whether we need to match. So this reaction takes the value, applies the fork function, which will give you either a left or a right. If it's a left, we're done, so we report the result using this report molecule that is given to us here. If we're in the right, it means we have subtasks. So for the subtasks, we define a new report molecule and an accumulator molecule. So the types are like this, as we decided. And the reaction for these report molecules for subtasks needs to accumulate all the results from the subtasks into the list. So that's easy to do. We consume the accumulator molecule, we consume the subreport molecule, and we add the new result to the previous list. So that's going to be the new list. And then we can check whether all subtasks are done here. Now this reaction is going to only run sequentially, so there won't be two copies of this reaction running at once. Otherwise, we can't guarantee that we are updating the value. So we are going to only emit one copy of accumulator. We emit that with initial value of empty list. Now, if everything is done, then we report. So we have accumulated all the partial results from all the subtasks we join them, and that's our final result that we report. This is our top level report. Otherwise, we're not yet done, so we need to wait for more subtasks to report the results. And subtasks report using this molecule. How do we make sure that subtask will report with this molecule? Well, we emit them. So for each subtask S, we emit a molecule start with the subreport on it. And so that's how we tell the subtasks to use the subreport molecule for reporting. So that's it. That's the entire code. And this function returns a start molecule. So it's ready to be used. Here's how we test it. We create a report molecule and a reaction that will help us test it. So this reaction is just for testing. It will consume the report molecule and a blocking molecule and return the reply to the blocking molecule to tell us what is that value. Now this is a very often seen pattern that you want to see in a blocking way. You want to see what is the value on some molecule. You make it react with a blocking molecule and reply. So let's do that. So these molecules are just for testing. This reaction is for testing. Now we run this. This will return us a start molecule, and then we immediately inject this start molecule. We emit it with some value and a report result molecule. So this will run, and then we emit the blocking molecule. So that will wait until it's done. So in this way, we wait until this entire fork join computation is done. So that's how it works, and the tests pass. Now, if we run this, we will find that this is very slow. This is actually much slower than the implementation based on futures. And the reason it is slow is that we are defining new reaction sites inside reactions. And we do that repeatedly in a nested fashion. So we have a tree, and each time the tree has a branching point, we define a new reaction site. And there is overhead when we define new reaction sites. Each site needs a lot of data structures. Static analysis needs to be performed. Unfortunately, this cannot all be done at compile time. Some of the analysis is done at compile time, but a lot of that analysis can be done only when we define the entire reaction site, and that is done at runtime. It is still done early. So for example, detecting errors such as live lock errors or static molecule usage errors. These errors are still detected at runtime very early, before any reactions can start. So it's better than waiting until reactions actually run and generate some errors. But it is still runtime. And so because of this, there is a significant overhead in terms of time. There's some significant number of milliseconds that needs to be spent on creating a new reaction site. Although the library attempts to optimize this, it's still somewhat long compared with just running a reaction. Once you define a reaction site, then running a reaction is quite fast, or emitting a molecule is quite fast. But defining a reaction site is not fast, and so we actually don't have good performance in this implementation. So to improve performance, we should use a single reaction site. We should not use a a number of reaction sites that's linear in the data, and that's what's happening here essentially. It's a number of reaction sites that we are creating is linear in the size of the data. So in other words, for the Fibonacci number is going to be exponential, because the size of the tree is going to be exponential in the argument. So a better way is to use one reaction site for all reactions. So how do we do that? Well, the idea is that we should, instead of accumulating the results using molecules, we should accumulate the results using data structures. Now, in Java, there are many data structures that we can use that are concurrent or thread safe. I'd like to avoid going too far into that direction, because then Java also has a fork join implementation of some kind, which is complicated to use. And the whole point of this exercise is to show how fork join is implemented in the chemical machine. So we don't want to use Java's concurrency libraries, but we do need to use some kind of synchronization mechanism here, because we need to allow several subtasks to finish at the same time and safely accumulate their results, and that requires certain kind of synchronization. In this implementation, we used this reaction for this synchronization. That's completely safe, but unfortunately, this reaction needs to be at a new reaction site, and so that's introducing a lot of overhead. So in this implementation, I will use Java's atomic integer as the basic synchronization mechanism. It's log-free, so it's very fast. And the main idea, I'm going to use continuation instead of molecule. So we have seen that molecules here that are used to report results, they're essentially used as continuations. Once you obtain your result, you call report on it. And that's similar to how continuations are used. Once you finished your computation, you call the continuation on that value that you just computed. So let's use continuation instead of molecules. That's the main idea here. Each start molecule will carry not a molecule emitter report, but a continuation, just an ordinary function. And this continuation will have the task of merging the partial results of subtasks when necessary. So whenever we split a task, we will create new continuations that we will put on the start molecules of the subtasks. Instead of here creating a new subreport molecule each time, we will create a new continuation, which is a closure, a function, very similar to a molecule, because it's still going to be called like a function, like this, to report the result. But it does not need a reaction site, and so it's going to be much faster. Now these continuations will need to collect and merge partial results, and that's a little bit of extra work. We have done this work here using lists, but this cannot be done concurrently, because lists obviously are not thread safe. You cannot append elements to a list from two different processes at the same time. So what I will do instead is I will introduce an array instead of a list, and put the data into an array. But all of that will be hidden, so we won't really see that. So instead of a molecule emitter of type A, I have now a function from A to unit. The molecule has this type, which is very similar to what it was before, except for this continuation. The consume result is a continuation. Now, previously we had a report result, which was a molecule. Very similar code. If the fork returns a left, we already report the result. Otherwise, we create a new sub-report continuation to put onto the molecules in exactly the same code as before, because, as I said, continuations are very similar to molecules in the way that they're emitted. Emission of a molecule is very similar to calling a continuation, except that it's concurrent and non-blocking. But this will be okay for us to have blocking continuation, because we're going to have very little work. We're just going to put data into an array. So how do we do that? We create a counter, which is going to be an atomic integer initially equal to the length of the subtasks array. So however many subtasks we need to wait for. Accumulator will be an array of that capacity, and subtasks will directly put their results into that array. Here's how. The new continuation is responsible for putting results into that array. So this continuation will be called by each subtask as that subtask is ready on its newly computed result value. So that will be the x. We decrement the counter. Now this is completely safe because the counter is atomic. So this can be safely done from different threads. Then we update the array. This is safe because we are updating it with different values of the counter each time. When the counter is 0, it means all subtasks are finished. And we are still executing in some thread, so let's just reuse that thread to run the join computation on it, which is sequential anyway. And then we report the result using the consume continuation. Other than that, it's exactly the same code. So very similar code, but we just replaced a list with an array. We added a counter, and we replaced molecules with continuations. So molecules would be safe, but they're just too slow in this case. And continuations are not safe, but we just organize this array update so that it is safe using the atomic counter, which will be every time safely decremented. So here's the test for this code. Is actually exactly the same API as before. So from the outside, it's not visible really that it's not a molecule. We can actually put a molecule instead of continuation because the molecule emitter has the apply method, so it extends the type integer to unit actually, and so we can just use it instead of a function integer to unit. We can use the molecule emitter, so we don't need to run extra code and create continuations. We can just use molecules instead of continuations transparently. So exactly the same test code. Let's run and see what the results are. The tests should all pass. The 8th Fibonacci number is 21, and we will see the timings. The timings of different implementations of Fibonacci numbers using fork join. I think I ran the wrong test. So let me run this. Need to wait a bit because we're testing with 25, so we are computing the Fibonacci number with index 25, and it's slightly slower. And here are the results. Sequential Fibonacci is, of course, the fastest, because for Fibonacci numbers it doesn't really make a lot of sense to do parallel computation. It's such a trivial computation that the overhead of parallelization is just too big to have any advantage. And so that's an interesting test of how much overhead we actually have. The computation itself is very small. How much overhead do we introduce by parallelization? And so we see that the implementation using futures is actually twice as slow as the implementation in the chemical machine and using the continuations, but implementation using local sites is extremely slow. Let me just run it again to see if this wasn't some kind of one-time effect, but basically that's what I would also expect. The implementation of fork join with local sites, where each reaction has its own local reaction site created for the forks, that implementation is just too inefficient. Yes, so very perhaps slightly different numbers here, but in principle the same thing. So the futures now are somewhat faster than the continuations. In my other tests, the futures are consistently slower, but that is certainly system dependent, and maybe my system is loaded now. I'm recording this talk. Right, so now I have very different results. This has become a little faster, this has become a lot faster. So very rough idea of performance, but nevertheless. So this is the best implementation with continuations. It took a little more work, but still the code is quite small. So this is the entire implementation of the fork join, and most of it is just declarations. So this concludes my presentation on the fork join in the chemical machine.